I'd like to welcome all of you here. Thank you for attending in person, and I'd like to welcome the people who are watching via webcast. I think today we're going to have an extremely interesting seminar. The title is, What Have Urban Experiments Taught Us About Atmospheric Flow and Transport? Today's seminar speaker is Dr. Julie Lundquist. She's a staff scientist in the Energy and Environment Directorate at Lawrence Livermore National Lab. Her research synthesizes observations of the atmospheric boundary layer with innovative data analysis methods and numerical simulations to improve our understanding and prediction of transport and diffusion in the atmosphere. Her work directly supports the National Atmospheric Release Advisory Center. She is particularly interested in the intermittent and inhomogeneous turbulence observed in urban and stable boundary layers, and so I think those are topics that are of great interest to those here at the Air Resources Board. For those who are viewing via webcast, I'd like to encourage you to submit questions. You can send them to Sierra, S-I-E-R-R-A-R-M. So it's like Sierra Room contracted at calepa.ca.gov. The email address is in the seminar announcement posted on our web. And with that, Julie?
Thank you, Eileen. Can everybody hear me okay, both here and online? Okay, great. Well, thank you, Eileen, for the invitation to come present some of our work today. It's always a great pleasure to talk about one's research with interested colleagues. So I'm happy to hear that not only will there be questions from everybody here in the room, but from people looking online. And I will be discussing some work that I've done at Lawrence Livermore National Laboratory in collaboration with members of my group, and we're the Atmospheric Transport and Fate group. In particular, I'll be talking about work done with Stevens Chan, Branko Kosovic, and Tina Chow. And Tina has now graduated from her postdoc at the laboratory and is a professor at UC Berkeley. So I mentioned before that I'm part of the group that looks at atmospheric transport and fate. And we're a group of research scientists who primarily support the National Atmospheric Release Advisory Center, which is a 24/7 operational center located at Lawrence Livermore National Laboratory. This center had its genesis in the 1970s, responding to incidents like the 3 Mile Island incident. So for several years, we were focused primarily on dealing with releases of radioactive material in the atmosphere. But in the last 10 years, and especially in the last 5 years, we've been expanding our attention to also consider biological releases that could be hazardous, as well as chemical industrial accidents, and of course, potential terrorist releases. Our center consists of a well-knit together team of operational meteorologists who actually work in the center, atmospheric scientists such as myself who do research that supports the models that are run in the center, and computer scientists who make sure that everything works well and help us find our bugs quickly so that we don't have any problems when there's an actual emergency. In addition to the emergency response nature of our work, we do a lot of other work that isn't sort of time sensitive and where lives are not directly in danger, where we do vulnerability studies and threat assessments to make sure that people who have critical infrastructure are prepared in the case of an accident or in the case of an attack of some sort. And being a national security laboratory, we also do some work with intelligence applications. So with this long list of tasks, you can see that we need to have a lot of expertise in a lot of different areas. So for example, we have meteorologists such as myself who are really interested in weather patterns and how we do a good job modeling atmospheric dynamics. But we also need to think about consequence assessment and what do we do with this information once we predicted a plume. So we maintain population databases where we look at how people move from day to night to figure out how people should be evacuated, if they should be evacuated, if shelter in place is an appropriate response to a certain kind of release. We maintain databases of critical facilities and the intricacies of atmospheric flow around certain facilities. And then, of course, we like to deal with data, and it's convenient if you have data that comes to you in tabular format with latitude and longitude and appropriate units of whatever you're interested in. But in many cases, we have to deal with data that's being collected in the field on the fly with people running around with canisters collecting things, or somebody's taken a satellite image. So we need to have the facilities, and we do have the facilities at hand, to synthesize these disparate data types together so that we can make a coherent picture of what's happening in the atmosphere during an event or before a suspected event, and guide emergency responders appropriately. So that's a lot of work, and no single individual has to do all that work, which is nice. And my work focuses on the research science and modeling efforts that support this operational center. We do a lot of different kinds of work, and today I chose 4 main topics to discuss with you. First, our field campaigns are very near and dear to my heart because I like to put on heavy boots and go outside and collect data. So I'll talk a little bit about our field work, and then how we use the data that we collect in the field to verify and validate our models, including our computational fluid dynamics models, which are very appropriate for urban modeling situations. When we want to provide reasonable boundary conditions or reasonable information about how the atmosphere is moving on the edges of our computational fluid dynamics models, we need to use high-resolution numerical weather prediction, so I'll touch on that work as well. And finally, one of the more interesting and not traditionally atmospheric science, but still very useful in this realm, one of these projects is our event reconstruction project, which assumes that, say you have 5 observations of something in the atmosphere, you don't know where it came from, you don't know when it was released, you don't know how big it is. How can we use that data in conjunction with our dispersion models and our meteorological models to create a picture useful for emergency responders to determine what it was, where did it start, and how do we respond accordingly? So I'll show a demonstration of how that is used in conjunction with both our computationally intensive models, the CFD models, as well as a simpler urban puff model. And as I said before, please do not hesitate to ask questions. So first, the field work. This is a picture of scenic Oklahoma City in the summertime. And I know that Sacramento is extremely warm in the summer, but Oklahoma City is really, really hot as well, and it's very humid. But we decided that July was a good month to go out into the field in Oklahoma City, primarily because in July the winds are mostly from the south. So if you picture Oklahoma, it's mostly flat for our purposes. You have a city in the center, and if you're trying to explore the effect of the urban environment on the atmosphere, this is a pretty good test bed, especially because the wind meanders a little bit, but not too much, and you can model it pretty well. So we at Lawrence Livermore and our colleagues at Los Alamos National Lab, Pacific Northwest National Lab, Lawrence Berkeley National Lab, Argonne National Lab, the University of Oklahoma, the Department of Transportation, and several other important agencies and universities assembled this field experiment, which we believe, and have not yet been corrected when we give talks about this, is the largest urban dispersion experiment ever conducted. So we had a passive tracer, sulfur, in this case sulfur hexafluoride gas, and we released it during several intensive observing periods in the downtown part of Oklahoma City. We did this both at night and during the day. We did instantaneous releases, which basically consisted of a large balloon filled with sulfur hexafluoride gas, and then we popped the balloon and it acted like an instantaneous release. And we also did continuous releases, which were half an hour of material being released from a hose. And we measured how this material dispersed in the urban environment, both with very fast measurements, taking measurements every 1 minute, or excuse me, every 1 second, and then with longer integrated releases further away from the source. Because if you think about all the agencies that participated in this program, we have a huge range of models for transport and dispersion. We have these super fast models that look at kind of gross characterizations, like what is the 30-minute dose in this one particular location, and we have other models that provide estimates every 1 second. So we wanted to collect data suitable for all these models to be tested and verified and validated. And in addition to looking at the transport and dispersion of this tracer, we also knew that we needed to explore the unique meteorology of the urban area. So we fielded thousands, it felt like thousands of meteorological instruments, but it was probably more in the hundreds as I'm adding up these numbers here, including lots of sonic anemometers, radar wind profilers, SODARs, surface energy balance stations, etc. And then finally, in collaboration with our colleagues at Lawrence Berkeley National Lab, we explored the efficacy of shelter-in-place procedures. And you probably know that in some cases, like if there's an accident at a refinery in Richmond, the warning will go out that people in a particular area should shelter in place until the cloud moves over. And they were exploring, if you're in a large building and you turn off the HVAC system, how effective is this really in protecting you from exposures to what was going on outside? So there was lots of interesting science, a traffic-induced turbulence study, lots of cool things going on, and I'll talk about some of those here with you today. One of the scientific questions that we wanted to explore was how good are our models really when we compare what we predict in model world to the real world. And the model that I'll be discussing today is called FEM3MP, which is our computational fluid dynamics model. We use this a lot before events happen and in preparation for events, for vulnerability studies and risk assessment. And we can actually use it in emergency response mode if we have a library of simulations prepared ahead of time. Right now the runs take a little bit too long to use if you have to have an answer in 10 minutes or so. But as we increase our computing capability, we hope to be able to use FEM for emergency response situations. So in the second bullet, I'm presenting the details of FEM3MP. It's FEM because it's a finite element model, 3 because it works in 3D, and MP because it's massively parallel to work on our big computers. And it resolves much of the physics that we think is appropriate to resolve when you're looking at simulations in an urban area. And while we do have big computers that we get to work with at Livermore, we still want to increase our computational efficiency. So we've developed a numerical shortcut, this mixed explicit virtual building approach that I'll talk about on the next slide. And we wanted to see if that was useful for applications when you're exploring dispersion in urban areas. The pictures here on the side are demonstrations of FEM's capabilities in the context of Salt Lake City, which was the predecessor experiment to this Oklahoma City experiment. And they collected a lot of really good data from Salt Lake City. One issue with Salt Lake City is that it's located right next to the mountains. And so distinguishing urban effects from all of the topographic effects and nighttime drainage flow made the picture quite complicated. And so in Oklahoma City, we hope to avoid some of those questions. But we still did some really cool simulations in Salt Lake City. So I mentioned the mixed virtual and explicit building approach. This top plot shows you the buildings that are located in the center of Oklahoma City. So this is defined as the central business district. Most of the buildings above 5 stories are represented here, as well as most of the densely packed large buildings. And we decided that these were the most important buildings to represent in our model. And we decided that the rest of the buildings in Oklahoma City would be represented not explicitly, not with cells around all of the walls, 1 meter size cells around the walls, but as roughness elements that are basically act like big trees in the model. And so in this top plot, south is on the bottom here near this large convention center, and north is up here. On this plot on the bottom, south is over here on the left, and north is over here on the right. And the buildings in pink are the buildings that you see up here. So you can see that in the actual computational domain on the bottom, we have a few explicitly represented buildings, and we have a lot of buildings represented just as roughness elements. So we saw this as a test of this mixed approach. There's a question back here? Okay, the question was, do we distinguish between aerodynamic roughness and... Yes, we are representing the roughness elements as aerodynamic roughness. Just we increase Z0 essentially, and if in the general urban area Z0 is set to 0.1, then that particular cell has something significantly larger. And I don't remember offhand what it is. So our test then consists of comparisons of observations to what the model predicts for certain cases. And these cases are called IOPs, intensive observing periods, and we had 10 of them with multiple releases within each IOP. And here I'm showing you a plan view of a simulation from one IOP that happened to take place at night. The pink things are buildings that are explicitly resolved, and the color contours indicate the speed of the flow simulated by FEM. This is a 3-dimensional model. Sorry, the question was, is this a 3-dimensional model? And the answer is yes, it is. So this is a 3-dimensional model. This is a slice at Z equals 2 meters. And the color contours represent wind speed, where red is high wind speeds, and I believe here the dark red is 15 meters per second, and blue is close to 0. And there are some white bars that probably don't reproduce very well. Perhaps they reproduce better online, that indicate the direction of the flow. And some of the intricacies that are characteristic of urban areas are represented very well here. So if we remember that the flow in Oklahoma City is always from the south in the summertime, we know that the flow is coming up from down here. And you'd expect to see channeling in this urban canyon and in that urban canyon, which is essentially what we see. But in the canyons that are perpendicular to the mean flow, we actually have counter-rotating vortices, where on the left side we have clockwise motion, on the right side we have counterclockwise motion. And up here, which is also really cool, in front of the Kerr-McGee building, which is the second tallest building in Oklahoma City, we actually have reverse flow because the wind is coming in from the south, hits the face of the building, shoots down, and then jets back out on the street. And living and working in an urban environment, you're very familiar with, you walk around a corner and the wind changes completely. And we can actually reproduce this in model world, which is pretty exciting. And it gets even better because we can actually reproduce it correctly some of the time. On this plot on the right, I'm showing predicted versus observed wind vectors. So the predictions are from the model, and they are the vectors in red. And the green bars represent the observations. In this case, these are averages from sonic anemometers at the appropriate time. And the gray buildings indicate, the gray boxes are buildings, and the color of the building indicates the height. So you can see that in many cases, we do a pretty good job of predicting what the flow is actually like within the urban area. And this is a typical agreement-disagreement that we saw when we look at most of the IOPs. There's a question? They are, in this case, the PWIDs were located on stoplight poles. So they were mounted up, so they were basically at, I think, 6 meters was the average, but some of them were lower because you have to use towers of opportunity in an urban area. I'm sorry, did I repeat the question? No? Okay, well, the question was where are the sonics, and I just explained that. Any other questions about the model data intercomparison? Okay. I mentioned before when discussing the overview of the field experiment that we released SF6 gas as well, and we can compare the predictions of that tracer dispersion with the observations. And in areas close to the source of the release, and we used different source locations, FEM is able to do a very good job in predicting the observed concentrations. So on the left, we have a plan view map of one IOP, IOP3. On the right, we have a different one, IOP9, with 2 different release locations. The release locations are not marked, but you can discern them by looking for the highest concentration of gas. So in this case, that's the source location, and over on the right, this is the source location. And you can see that some of the interesting features characteristic of urban areas, like a plume splitting around a large building, are both represented well in the data, which appears these small boxes filled with colors, and by the model predictions. So the large contours are the model's predictions of where the tracer gas went and what concentrations would be seen there. And the small colored boxes use the same color scale and show what the observations showed. Is there a question?
Yeah, I noticed that your rooftops don't have any tracer concentrations. Were they not measured on the rooftop?
The question was, I'm not showing any rooftop concentrations, and did we take any measurements there? Actually, for this plot, I don't show any rooftop concentrations, but in some locations we did use multiple levels to collect concentration measurements. And some very interesting phenomena showed up there. Like in many cases, we had very low concentrations close to the surface and very high concentrations aloft. So there's very rapid vertical motion in urban areas, as we would expect. And that can be represented. And I don't have any slides with me that show the model data intercomparison for those cases. But the agreement was not quite as good, but it was still acceptable. Yes, everything is set relative to a reference level of z equals 0 because the slope in this part of Oklahoma City is extremely subtle. I think it's a 2-meter difference from pretty far south of the beginning of our domain and pretty far north. So, yeah. Okay, the question was if we're not using terrain following coordinates. So the building heights are relative to the ground, essentially, and we assume that the ground is perfectly flat, and our height coordinate is z, not eta, or any other pressure variable.
So that's why buildings, because you're talking about 2 meters above ground level.
Right. The question about buildings and terrain following coordinates connects to something else that I will discuss later in our talk about how do we appropriately represent buildings in different kinds of models. So I'd like to come back to that issue later. And there's some really exciting, well, I think it's exciting work that we're doing. But please be sure to ask me the question again when we get to that point. Okay, so what I wanted to convey in this slide was that in addition to capturing the meteorology in the downtown urban area, we also do an acceptable job of reproducing the dispersion in the downtown urban area for the cases that I'm showing here. And we have some journal publications that discuss all of the IOPs. So there could perhaps be other regions in which we don't capture all the relevant physics. And so when we look further away from the sources, so further out of the intense urban complex and out into the more kind of mixed rural urban buildings where most of the buildings are maybe 2 stories tall and less densely packed, we see different types of behavior. So here I'm showing 2 plots from 2 different IOPs. Concentrations are on the y-axis, and distance downwind is on the x-axis. The distance downwind extends from 0 to 2.5 kilometers in both cases. And I am trying to illustrate here that when we're close to the source, we do a really good job, as we saw in the previous plot, of capturing the variability that we see in that urban area. But as we go further downwind, there's considerable deviation between the observations and our predictions, both in high wind speed cases and in low wind speed cases. So this implies that there's some physics going on that we are not representing in our model that it needs to be incorporated somehow. Okay, question? Okay, the question was, is our disagreement or lack of disagreement contingent on how we placed our samplers and relative to the buildings? Yeah, and we tried to avoid putting them too much in the lee of buildings unless we were specifically trying to test our ability to capture lee vortices and that kind of stuff. And there could be individual isolated effects that contribute, individual isolated buildings that could contribute to this. But the plots I'm showing here are representative of all the other IOPs. And so the fact that there is missing physics was borne out in several of our investigations. And so that motivated us to explore further what is the other physics that we need to be capturing. So we get to collect more data, which is always fun. The pictures that I'm showing here are of the Livermore Crane Pseudo Tower, and this is a unique meteorological platform, and I don't know if it will ever be replicated again, but I think it would be pretty cool if it was replicated again. We used a construction crane that was located north of the downtown area, and we put a massive weight at the bottom of the tip of that crane and put essentially a ladder with a lot of tension there, and then mounted 8 sonic anemometers along that crane. We needed to be able to get vertical, and we needed to be able to be vertical downwind, and we needed to have a relatively small footprint. So in urban areas, you have to do a lot of unique towers of opportunity, and this is one of them. And the data actually looked really good, and we were very pleased to be able to use it for a lot of high-resolution turbulence studies, in fact. On this plot, I'm showing a slice at 50 meters of FEM3MP TKE contours, so turbulence kinetic energy contours at 50 meters, to illustrate the fact that the buildings in the urban area generate a pretty big wake that decays downwind, and that this crane location tended to be either at the end of the urban wake or just outside of the urban wake. So if we're trying to explore what's happening downwind of the urban area, this is well situated to help answer those questions. And again, we used sonic anemometers collecting data at 10 hertz so that we could explore fluctuations in TKE. And we've done a lot of data analysis of that high rate data, and some of those data are shown here. Not everybody may be familiar with TKE budgets, but we can make a budget. Since turbulence is a conserved quantity in the atmosphere, we can make a budget that says that it's produced, or it's dissipated, or it's stored, or it's transported. And we can figure out how big each of those terms are, and then figure out what physics is going on to cause each of those terms to be large or small. So what I'm showing here are profiles. Each of these is a plot of TKE on the x-axis versus height on the y-axis, where we use the data from that crane to break out each of the terms of the TKE budget. So for example, the black line with no symbols is the storage term, the time rate of change term. Purple is the production of turbulence by shear. Red is the production of turbulence or the suppression of turbulence by buoyancy. Blue is TKE dissipation rate. Green is turbulence transport, vertical turbulence transport. And the black line with squares is a very interesting line. That's the residual term. And it also includes the advection of turbulence. So when we make calculations like this, there are a lot of assumptions that go into it. And we have to be very careful to carry those assumptions all the way through so that we have some estimate of the error in our measurements. So all of the error plus this movement of turbulence from one location to another is included in this black line, the residual term. And when we did those error calculations, the error is only less than 10% of what we actually see here in this line. Now, these are urban profiles. And I've done a lot of rural work as well, away from buildings, and so we're just sampling kind of the rural atmospheric boundary layer. And you never see an advection term that large in a rural environment. And so this is something either very characteristic of bad data, which it's not. We've done the checks to make sure that it's not characteristic of bad data, or something very characteristic of an urban environment. And that latter hypothesis is what we're arguing here, that in an urban area, in the urban matrix, you have a lot of generation of turbulence. Flow goes through and around buildings. You get a lot of vortices. Lots of turbulence is produced. As you move downwind, it dissipates. But that movement of turbulence downwind, at the downwind location, it's the stuff that came from upwind that's important, not what is being generated downwind. So this argues that in all of these cases, the black line is the biggest line on the production side. This argues that if we're trying to simulate flow in the urban environment or just downwind from the urban environment, we have to use a turbulence model that accounts for that inhomogeneous production and dissipation of turbulence. So most turbulence models have an assumption in it that within a given grid cell, the production and the dissipation of turbulence is equal. And that's not true when we're looking at urban areas, especially at high resolution. So if the crane and if the big urban complex were all in the same grid cell, everything would be peachy because the pluses and the minuses would add up to zero, which is what they should do. But when we run high resolution models like we're doing, especially at 400 meter resolution or even 133 meter resolution and what we're going down to, we have a problem with our turbulence models. And so this is something that we've identified that needs to be fixed. And should you want more details, you're always welcome to ask me questions about this. We also have a journal publication that came out last month in the Journal of Applied Meteorology that also discusses the details. So we need to fix our turbulence models. We can also explore them, explore how turbulence behaves downwind by using information from the CFD model. We can take our domain and chop it up into 4 kind of gross regions: the upwind region that shouldn't have any urban effects, the central business district with a lot of urban effects, and then 2 decaying regions, the urban shadow and urban wake. And we can look at how TKE, which is on the y-axis, increases and decays as we go downwind from the urban area. And we see that the decay rate of turbulence is directly proportional to the incoming wind speed. So these 2 plots on the left have relatively low incoming wind speeds at 5 meters per second, and the bottom right one is the highest wind speed case, 7.2 meters, and so you see that the atmosphere never really recovers from the urban effect in the area that we're simulating. So this means that we can use our CFD model that just focuses on urban areas within the central business district without a problem. We're able to get the meteorology, we're able to get the concentrations, and the urban generated turbulence is the most important thing going on. So in this region, in the central business district region, that's fine. But when we start to go downwind, there's room, the turbulence is decaying, so there's room for other physical processes to come into play that are important and must be parameterized. And these processes include mesoscale phenomena like nocturnal low-level jets or other ways that turbulence can be produced. So that brings us to the question of how do we connect those mesoscale phenomena, those weather phenomena, with urban simulations, since urban simulations tend to have a difficult time incorporating changing boundary conditions, which is what you need to do if you are trying to study nocturnal low-level jets or what fronts moving through and things like that. So we are working with a numerical weather prediction model called WRF, the Weather Research and Forecasting Model. And you might be familiar with this model. It's a community-developed numerical weather prediction model. When you download forecasts from the National Centers for Environmental Prediction, you're getting WRF output now. They used to use a model called ADA, and now they've switched it to WRF. And these models are typically run in nested mode. So you start with a big part of the world, and then you run it at coarse resolution. You feed that information down to a smaller domain and provide that boundary conditions and use smaller and smaller cells as you nest down. But the problem that we identified before, when we get to really small nests, like 400-meter sized cells, then our parameterizations break and don't work anymore. So we have to change the physics that we represent. Additionally, the coordinate systems, and this is in reference to the question that you asked before, especially if you're using terrain following coordinate systems, you can't capture the complexities of the urban environment. Because if you have a terrain following coordinate that needs to go up the side of a building, height above the surface when the surface is vertical doesn't really, it does not compute. So we have a problem, and we're trying to figure out how to address it so that we can provide appropriate boundary conditions to our CFD models so they can work in all domains, the central business district as well as the urban wake and urban shadow regions. We can show with the data that we collected in Oklahoma City that the errors that we get when we're sloppy about feeding boundary conditions to CFD models are pretty considerable. So shown here are two plots of observations versus model. The left plot is wind speed, the right plot is turbulent kinetic energy, and they're both on an axis of 1 kilometer. So this is 1 kilometer on the y-axis. The red and blue lines are model outputs, either WRF, the numerical weather prediction model in red, or FEM3MP, the blue line is the CFD model. And then the black lines that we see are either data from radar boundary layer wind profilers on the left, or turbulence measurements from the crane tower that I talked about before on the right. And you can see that WRF, the weather prediction model, does a good job at capturing the weather, which is what it's supposed to do. The red line matches the black line over here. But when we're thinking about how stuff disperses, or nasty stuff, or how anything disperses in the atmosphere, we need to capture the turbulence appropriately. And neither WRF, the red line, nor our CFD model, the blue line, can match our observations. So we need to modify how WRF captures turbulence, but we still need to use WRF's ability to capture the gross features of the weather. And so we have an internally funded research project at Livermore that is funding us to expand WRF's capabilities by modifying its turbulence parameterizations. And we are also modifying how WRF deals with complex terrain by implementing something called an immersed boundary method. So this is a feature of CFD codes, or computational fluid dynamics codes, that are typically used for modeling things like how ink disperses in a laser jet printer and that kind of stuff, where you use a Cartesian grid and you have points both inside and outside of your terrain. And you do some calculations across the terrain in order to make sure you're still getting the physics right. And we're in the second year of this third-year project, and at the WRF workshop at NCAR in Boulder earlier this summer, we presented some initial results of both the turbulence modeling and the immersed boundary method work, showing how we're beginning to make improvements in WRF's capabilities. I think there's a question.
I just wanted to know, did you use the TKE from the WRF as a boundary condition for your fluid dynamics model?
Okay, we did not use the TKE from WRF as a boundary condition for the CFD model. We have done that in the past, but we did not do that for these particular runs. And it would have been a really bad idea to do that. What we did use for boundary conditions just came from observations. But you can see that what WRF shows for TKE has not only the wrong value, but the wrong shape. So yeah, we try to stay away from that. We used an observed upwind profile for boundary conditions. Peter, can I assume that if somebody has a microphone, I don't need to repeat the question? Okay, good. Okay, so I mentioned that we're showing improvements in what we get with WRF with our modifications. We started with the easiest possible example, and that's what this is here, a neutral boundary layer flow. And as this is an analytic solution, so we know that the black line seen here is the analytic solution to this very simplified scenario. And we want to have a wind profile that follows a logarithmic increase with height, and that's what the black line represents here, because this is normalized height on the x-axis and wind speed normalized on the y-axis. So that's the goal, is to hit the black line. The blue line and the light blue line represent the two turbulence parameterizations that are currently available in WRF, and there's divergence close to the surface and considerable divergence aloft. And when we implement this DRM turbulence model, which stands for the dynamic reconstruction model in WRF, we are able to achieve much better agreement with the log law analytic solution, both close to the surface and aloft. And this is ongoing research, so we're continually fine-tuning parameterizations, and we're doing some tests of flow over simple hills and that kind of stuff. And we'll be showing those results at the American Meteorological Society's urban meeting in September. So I'm not supposed to show them now, but it's really tempting, because it's exciting to be able to make these changes to address a problem that we've seen in the model. When we look at slices of the model domain, we can make contours of turbulence and how turbulence behaves in the domain. And that's what we have here. We have 3 slices from 3 simple runs. I believe they're actually from the same neutral boundary layer flow that I showed on the previous slide. These are contours of TKE with about the same range, from 4 meters per second to 8 meters per second in the color contours, with the 2 WRF native closures, the Smigrinsky and a TKE closure, and then our improvement. One of the problems with the existing TKE closures is that these streaks start to form and then propagate through the domain, and we're able to avoid the generation of those streaks when we use the dynamic reconstruction model on the right. Okay, so that addresses what we're doing in the realm of high-resolution numerical weather prediction. And finally, I'd like to talk about how we deal with cases where we need to reconstruct a missing source. So an accident or an attack or something like that happens. We have a few measurements taken. We know what the meteorology is. How do we figure out where the source is? How big was it? And then what do emergency responders do? How do they respond? So I will talk about that now. And this is, again, based on Oklahoma City. So this is a picture of the domain. I believe this was taken from Google Earth. And the green diamonds tend to represent about where the sensor locations are. And if this pink line is the source, how do you use information from these sensors? If you don't know that that pink box is there, how do you use that to figure out where the pink box was and then what the appropriate plume dispersion is? Or is that even possible? And because I'm here today talking to you, it kind of takes the suspense away, that we can do it. To explain our process, I'll start with a prototype example, and this is just flow around a cube. So in this case, the flow is coming from the left. We have a source that we've posited here, the pink box. It's dispersing material that goes around the cube with high concentrations on the top, or in this case, it would be, as you face the box, it would be on the left, and relatively low concentrations on the bottom because it's slightly asymmetric. So if this box was at one grid point below, then this flow pattern would be reversed. So what we have to work with are data points from these 4 sensors. So starting from that, how do we figure out where the source was? We initially propose an initial solution. So we say, okay, let's pick this yellow box. We'll put a star there. We'll guess the concentration. We'll release material, and we'll let it run forward. And we collect data at those 4 places. And then we compare we compare those data to the data that we have actually observed. And then we move on to another location, this second star here, and say, okay, let's do a forward simulation from that location with a different concentration. How do those data at these 4 places compare to what we had before? If this compares poorly, as it does in this case, then we go back to our initial location and take a small step through the domain somewhere else. We do another forward run, compare those data, accept it, say we like this one better, that becomes our new starting location, and we move on and march through the domain. And as you can imagine, this can be kind of computationally expensive, but we also have shortcuts that we can use for that and do all the runs ahead of time and then do our evolution through the domain relatively quickly, actually. So we have these Markov chains, because this is a Markov Chain Monte Carlo simulation, moving through the domain, and then when we do the simulation for real, we end up with a tangled mess that looks like this. When we distill the information that comes from that, we actually end up with a probability distribution of where is the source most probably located. Where is the source that is most consistent with the data that we have collected from these 4 locations? And the advantage of this is that we get a probability distribution where we don't say that the most likely location is here. We say that this is pretty likely, but these other locations are also possible. So if you have the resources, you should investigate those. A lot of source inversion methodologies try to find a single best answer, and we're not in that business. We want to figure out what is the most likely field of possibilities so that we can respond to all of those events. There's a question? For this, the question was, do we need to assume a constant source? And the answer is no, you don't need to. For this example, we did. But we've done some other examples that involve sources that start and stop, and you have to guess or invert for the initial time and the final time, invert for the release rate. And then in one really interesting example, we have a moving source that we try to identify. And I didn't include those slides, but that's also a really fun simulation to look at. So we end up with a probability distribution we end up with a probability distribution of source location where there's one cell that is right next to the actual source that has a lot of probability mass and a lot of other cells that have some probability mass. Similarly, we look at the release rates, and we have a distribution of possible release rates. And in this case, the peak also corresponds to where the actual release rate was in our simple example. We can also aggregate that information together from all of those possible release locations back here and all of those possible release rates into a most likely plume. And this is what we found emergency responders are very interested in, because they don't really care exactly where the source is and how big it is. They want to know where the stuff is going and who do they need to get out of the way. So we can make a composite plume that says that we're 90% confident that of all of those scenarios, there will be a lot of material in this red area and almost no material in this green area, and it will decay in this fashion. So that was our simple example, and we can move on to the demonstration of Oklahoma City. So you may recognize these buildings now from the simulations that I showed before. These black diamonds represent the sensor data that were actually collected in Oklahoma City, and the pink box is the actual source. And then some information about the simulations is over here on the left. Now, as I showed before with the FEM simulations, there's a lot of complexities in urban flow, and we have plumes splitting as they go around buildings. We have vortices behind buildings, and we also have the ubiquitous model error that can be incorporated in our event reconstruction methodology. So when we make those steps and compare the data that was actually collected to our model forecasts, we can include an accommodation of we're very confident in our model or we're not so confident in our model. And that helps us decide as we march through our distribution of which points should be considered. So when we do this inversion, we do 20,000 forward runs usually of the plume dispersion model. And a forward run is each of those steps where you move to one location, release something, and compare it. Now that is incredibly expensive with a model like CFD. When we're using cheap models, we do that easily. I was telling Eileen earlier today that we had a summer student a few summers ago working with a PC that was already 10 years old, and she was able to do all of the Oklahoma City in one weekend. She wasn't there, she just let the computer run over the weekend. And she was able to do that very easily with a cheap computer. But for CFD, we need a different approach. So we implemented a Green's function approach, which basically lets us scale our forward simulations so that we don't have to do them all. We just do all locations and then scale the concentration. And it still took half a day on a large part of Livermore supercomputers. The Markov chain path, the exploration of physical space that our chains went through is shown here. And again, in pink, we have the actual source, and you can see that all of the chains converge pretty quickly to the actual source location. And when we zoom in on that area and we look at the probability distribution, we have this checkerboard pattern, which is one of our computational shortcuts. And we find that our most probable source location was within 50 to 100 meters of the actual source. So considering all of the possibilities for model error, we were quite pleased that we were able to get the source location so close, especially in an area that had some complex not interference, but some complex physical processes to represent. And when we look at the release rate histogram, we also see that we were able to get very close to the actual release rate. And so we consider this example a success of the demonstration of this event reconstruction capability with our CFD model. Now, I mentioned before that we have in our operational center, I'm sorry, there's a question?
Just clarify, did it take you half a day for 20,000 runs?
It took, no. We did not do 20,000 runs. We did 128 forward runs. If we did this the normal way, it would have been 20,000 runs. We did 128 forward runs by taking our domain and saying we're not going to do a release at every point. We're going to do a release at, I think it was 1 out of 4 or 1 out of 9 points in a box. And then we scaled all the release rates. So we just did a constant release rate for the whole thing, and then assumed that if we wanted to do in the inversion a lower release rate, then we would just scale it. And that's a reasonable assumption for this type of release. So for 128 forward runs, that took half a day on about 1,000 processors. Okay. So that was a demonstration of how event reconstruction would work with the CFD model. We've also demonstrated in an urban area. We've also demonstrated event reconstruction with the continental scale radioactive release. And this was an event that was based on an accident. A steel mill in Spain accidentally melted down some medical equipment, and so they released some cesium that was noticed 3 or 4 days later when it got to Italy. And this is called the Algeciras release because it turned out that the source was located close to Algeciras, Spain. And we've been able to do an event reconstruction of that using these data, these red points, and honed in on the source in southern Spain. We've also used data from a regional dispersion experiment. This top right plot represents the Copenhagen tracer experiments, and we've used data from these blocks or these lines of sensors to reconstruct a source there. This set of simulations was interesting because we actually broke some sensors, had them report flawed data, and we were still able to do the reconstructions. And if you will ever invite me back again, perhaps I'll talk about the Copenhagen release, because all the permutations that you can go through with trying to make your data look like real data that is flawed, it's nice to be able to still reconstruct the sources, even with flawed inputs. And on the bottom right, I am showing a plot of Oklahoma City with a very simple urban dispersion model, UDM, the urban dispersion model from the Defense Science and Technologies Laboratory. And we were also able to do that reconstruction as well, with some loss of accuracy because we were using a simpler dispersion model. So we regularly try to make sure that the scientific advances we make in our modeling group propagate into the NARIC Operational Center. So we use our CFD simulations for improving the urban parameterizations that are in our faster codes that we use regularly for dispersion. We're currently using that mixed explicit and virtual building approach in our assessments for exercises. And we're trying to get more computers to use in our center so that we can use our CFD model for emergency response. Currently in the center, we're using standard WRF, the numerical weather prediction model, for providing input to our dispersion models. And we are developing the capability to run our improved version of WRF in the center so that we can have that high resolution and more correct turbulence parameterization available for our emergency response. So we like to use data, we like to collect it, and we like to use it to improve and validate our model's performances, and then learn some interesting things about urban boundary layers as well. And we also are working very energetically on improving NWP models And this is a modification that we're not making just for what we do at the lab, but we're hoping to have our work included in the next WRF release, which should come out in March of 2008. So one of our staff members will be going to NCAR to work with them on implementing what we've done there. And then we also like to use our data to test our data assimilation and sensor data fusion methodologies like event reconstruction. So if there are any questions, I would like to answer more of them. I think there's a microphone coming around.
When you set up your field experiment with the crane, was the crane itself actually downwind of the line that had all the sonic anemometers on it?
Yes, the crane was to the north because we knew that the flow was typically from the south. So we put the crane itself upwind or downwind of the sensors because we didn't really want to explore flow through the crane. We wanted to explore the urban area. The comment was that I used the term urban boundary layer with improperly because
well, it's not improperly. Just I'm trying to put it in the context of classical meteorology.
Yeah, in classical meteorology, we usually have the urban boundary layer or a convective boundary layer and a stable boundary layer. And we've started using the term urban boundary layer in our work because we see things in urban areas that don't conform to what you would normally expect from a surface layer, a typical surface layer, or a typical convective boundary layer, or a typical stable boundary layer. And we're finding that the things that you might expect in those canonical cases you never see in the urban boundary layer. And that's the deviation that we see is even beyond what you normally see in real life versus canonical cases. And so we just use urban boundary layer to denote anything in an urban area that's probably not typical of what you would expect from a textbook example. So it's true that in urban boundary layers you can often develop what the CFD or the fluid dynamics people would consider an internal boundary layer, and then you have constant flux zones. But even the idea of having a zone where you have constant flux with height, that's not really borne out by observations. As we've discovered with the Oklahoma City data, and as our colleagues in Britain have discovered with their urban experiments, the bubble experiment, there was some really nice work done on urban flux profiles there. So yes, urban boundary layer doesn't have its own little category. It's just kind of a catch-all phrase for all the interesting messes that we encounter in urban areas.
Were there simple dispersion models that would be based on limited measurements of TKE? Have you looked at any implications from the Oklahoma City experiment for some of the operational models that people are using?
Right, okay, so there are very simple models that say that if you have one observation of TKE at this point and assume that it's representative, then how would your material disperse? And I have not done those intercomparisons with the Oklahoma City data, but Steve Hanna has been doing that. He has a class actually at Harvard that did a lot of work with that. And then I think Akula Venkatram is also doing some of that work with the Oklahoma City data. Because for the first 2 years, the data were protected, but now they're publicly available. So that's available. We haven't done any of that work at Livermore.
And so would they be developing criteria for where the TKA measurements would be made and how many would be needed to represent?
That's an important ability to have, to know where to put your observations. And my understanding is that there is no agreement yet as to where the best site is. When we did another urban dispersion experiment in New York City, we again had the problem of we have a few observations of TKE. They're very different in this very small region, and which one is representative? And emergency responders needed guidance for not just TKE observations for dispersion, but wind observations. Like, do you want to get on top of the tallest building to get your measurement? No, because that's not necessarily going to tell you what's happening at the ground. And I don't think there's a clear consensus yet of exactly what of exactly where these measurements should be taken best. It depends on your purposes, because if you're looking at, or I would argue that it depends on your purposes. Because if you're looking at an episode, a specific episode of dispersion from one particular location, and if you want to predict the plume that comes from that, then obviously you want to have your measurement as close to the source or as close to your downwind locations of interest as possible. But if you're interested rather in a more global picture, like an integrated assessment for a particular area, a different location is going to be more representative of what you're interested in. So I think the proper thing to do would be to throw a bunch of big computers at it and do a lot of simulations and figure out, if I extracted a profile from this location, is that useful? And if I tried it from a different location, is that more useful? And there are statistical experiments you can do, OSSI studies, optimal, I can't remember what OSSI stands for, but it's a way of determining where you want your observations taken from. And doing those sets of studies with big simulations is, that you have confidence in, that's probably the best way that I would approach that problem. Thank you for your attention and your interest.